Okay, great. Okay, so it's great to have Geoff Penington from Berkeley. He's going to talk about his work on leading order corrections to the QES prescription. Please go ahead.
Okay, thanks very much indeed for inviting me to talk. So this is some joint work with Chris Akers that we should hopefully be submitting to archives this morning. So it should be appearing in a couple of days. Okay, so just very boring review slide. ADS-CFT is a duality between a conformal field theory on the boundary and a load of fishes in the bulk. And these fish are all the same size. There's anti-de Sitter space in the bulk. Hopefully everyone is familiar with that. But you know, one of the things that we want to do in ADS-CFT is to understand the dictionary that relates objects on the two sides of duality. And there's one sort of element of that dictionary that's been particularly important over the last 10, 15 years, which is, in its original definition, the Ryushaki-Nagi formula. So what does this formula say? It says if you look at some boundary subregion and you look at the reduced state on that of the boundary theory on that subregion, then the entanglement entropy of that reduced density matrix is given by the area of the minimal bulk surface that is anchored on that boundary region, technically that is homologous to that boundary region. This formula is pretty cool and it's been very, very influential, but it you know, that's just the sort of leading order like classical contribution. You also need to include quantum corrections, and those quantum corrections just come from entanglement between quantum fields in the bulk that are entangled across this surface. More generally, it just comes from the Bohr-Neumann entropy of all the bulk quantum fields in this region, between the boundary region and the minimal surface. So yeah, heuristically, what this means is that if this blue fish here is entangled with this blue fish over here, then their entanglement entropy contributes to the entanglement entropy of the boundary in exactly the same way that the area term would, classical area would. So this is called the quantum extremal surface prescription once you include these quantum corrections. And you know, this is not just a pure conjecture pulled out of nowhere. This can be derived by using gravitational path integral in the sort of low energy bulk effective action. And it's led to a number of big successes, including last year getting a derivation of the page curve for the Hawking radiation of an evaporating black hole, agrees with unitarity. Okay, great. So that was sort of just background I needed to even define what I'm going to be talking about in this talk. So let me now give a sort of summary of what this talk is going to be about. Basically, I'm going to be arguing that if you just, even though this rule for computing entropies has led to all these huge successes, then if you just apply it like, completely naively without thinking about the state that you're applying it to, then you actually get paradoxical results. You get contradictions between the results you find in different states. And in fact, these paradoxes already exist, even if you just treat the quantum extremal surface prescription as giving you the leading order 1/G Newton answer for the entropies. Even if you just assume that there can be corrections at all orders after that, that's not enough. These paradoxes already exist, contradictions already exist. So something needs to be changed about this prescription, even at leading order. The qualitative change, not just a small correction. So one example of the states where you can see these paradoxes is indeed evaporating black holes. Exactly, very closely related to the examples, the ordinary examples of quantum extremal surfaces for evaporating black holes that people now know and love. But yeah, but it's not just in those situations where these problems show up. You can also see them in cases where there's no black holes at all. The second major point is that if you do the entropy calculation more carefully and include a larger family of saddles when you do the calculation, then you do actually get consistent results that don't have any contradictions, but don't agree with the quantum extremal surface prescription. And what you can see is that the difference is coming from the fact that there's this famous assumption made by Lukowitz and Maldacena in their original derivation through the Takinagi formula, basically that you only need to consider one saddle for each value of n in the replica trick. And that derivation just causes you, that assumption and derivation just causes you to get the wrong result. If you make it, you get the QAS prescription. If you don't, you get the sort of right answer, which is very different. So this leads us to find a sort of general set of results for what the naive QAS prescription needs to be replaced by, which we call a refinement of the naive QAS prescription. And these results are defined in terms of what's called smooth min and max entropies. So these are sort of like the von Neumann entropy for many states, but in general, they're not equal to von Neumann entropy. There's a generalization of it. And they play this very important role in what's called one-shot quantum Shannon theory, which is really just the information-y part of quantum information theory applied when you have a single copy of a quantum state, as opposed to having a large number of copies of the same state. Since this is exactly what we have in ADS-CFT, it shouldn't be surprising that these sort of quantities show up. And finally, going to see that sort of all these results, and in particular the consequences it has for the notion of when you can do entanglement wedge reconstruction. Basically, again, that should be defined in terms of like smooth min and max entropies rather than von Neumann entropies. All these results are actually very closely related to a particular, very common quantum information task from one-shot quantum Shannon theory, which is called one-shot quantum state merging. So I'll hopefully explain how that sort of reinterpretation of entanglement wedge reconstruction works and how it's helpful to see what's going on. Okay, great. So the sort of first part of my talk is I just want to get across this idea that the naive QAS prescription does not work in general. And the situations where this will be true are situations where you have sort of two quantum extremal surfaces. Sometimes classical extremal surfaces will be enough. And you also have a large amount, an order 1 of G Newton amount of sort of bulk entropy sitting between them. So one case where this happens is obviously evaporating black holes. But another case is just if you look at a boundary region B that consists of sort of two intervals in ADS3 CFT2. So in this case, we always have sort of two extremal surfaces that are respectively, let me just deal with this. These two extremal surfaces are sort of homotopic to the region B, this surface is dashed, and its complement region B prime, B bar, which we showed in a solid line. Okay, so these two surfaces always exist. And what we can then do is we can add some matter. This blob sitting in the middle should be thought of as matter. And the energy density of this matter is going to be order epsilon over G Newton. Okay, so epsilon is going to be sort of a small but order 1 number. And then we're going to work in the semi-classical limit where G Newton is very small. So depending on how you scale your energies, then this can either be thought of as a small amount of energy or a large amount of energy. But the important point is that its back reaction on the geometry is small. That's because the Einstein equations have a factor of g Newton in front of the anti-momentum tensor. Okay, so up to perturbative corrections, the geometry of this space-time just looks like the ADS3 vacuum. If all this energy is just some bulk fields that are sort of thermal in a mixed state, then the entropy of the bulk fields will also scale as order epsilon over g. In particular, this means that if we sort of tune the size of our region B, so it's very close to sort of being half the entire boundary, then we can set things up so that sort of the area of this surface gamma 2, these two dashed things, is bigger than the area of solid lines gamma 1, but it's smaller than the area of the solid lines gamma 1 plus the sort of potential thermal entropy of this stuff in the middle. Okay? In particular, you know, we don't need to tune this. We need to tune this at order 1, but we don't need we don't need to get ever closer to being exactly half the region as g Newton goes to 0. So it's not a lot of fine tuning. This is a reasonably generic thing that can happen. Okay, so we're now able to construct a paradox, and it's really very simple at this point. We just consider 3 states. Okay, the first state is going to be when we have all this matter just sitting in some pure state. Okay, in this case, then the matter has no von Neumann entropy, and so it doesn't contribute to the generalized entropy of this surface gamma 1. And so the smallest generalized entropy surface is just gamma 1, and we find that the entropy of the region big B is just area 1 over 4 g Newton. Okay. Second state we're going to consider is just going to be a thermal state. Okay, so now the generalized entropy of this surface gamma 1 is area 1 plus this extra entropy S, which we've constructed things so that that's bigger than the area of the dashed line, area 2. So now that becomes the minimal quantum extremal surface, and the entropy of the boundary region big B is area 2 over 14. Okay, all fine so far, but now we're going to add in our third state, which is just going to be a mixture of these two bulk states. Okay, so you know, the bulk entropy of the mixture of these two bulk states up to some small correction is just given by the probability of it being in the thermal state times S. Okay, so 1 minus P times S. So then the QES prescription says that the entropy of the boundary region is just going to be given by the sort of smaller of the two candidate quantum extremal surfaces. Right, so in this case, the smaller of area 1 over 4 g Newton plus 1 minus P times S, and area 2 over 4 g Newton. Okay, they're the two options, and you just have to look for the smaller one, and it's just equal to that. The other one is irrelevant. However, if our bulk state is a mixture of these two states, then our boundary state must also be a mixture of those two states, and hence the reduced state on region big B must also be a mixture of those two states. Okay, so the state rho big B has to be a mixture of P times the state rho B for the pure state plus 1 minus P times the state rho B for the thermal state. Okay, and again, very standard bounds on the entropy of a mixture of two states mean that it just has to be the case that, you know, assuming our results for the entropies of the pure state and the thermal state were correct, that the entropy of this mixture of the two is just given by P times the entropy of the pure state plus 1 minus P times the entropy of the mixed state, plus at most something that's order 1. Which really comes from potentially you can have a Shannon entropy term from mixing the two, but that's pretty small. So, you know, up to that small correction, then it's just given by this formula. Okay. It should be very easy to see that if I plug in, say, P equals 1/2, then these two formulas give very different answers, right? In particular, you know, for big enough P, then this thing just gives the answer A2 over 4G Newton, whereas this one is still a sort of weighted average of A1 and A2. Okay, so it's going to differ, and more than that, it's going to differ at order 1 over 2. So there's our paradox. It's really quite simple. And, you know, I claim that the state the quantum extremal surface breaks down for is this third state, the mixture of the pure and thermal state. It's not the pure state or the thermal state themselves. So you might sort of object, like, how do I know that? Like, couldn't it be one of the other two? And the answer is because we're going to calculate it and we're going to find that that's the one that changes. But for the moment, I just want to give a bit of intuition about what is special about the mixture of the two states that isn't true about the pure state or the thermal state on their own. Okay. So if I have some thermal state of a large number of degrees of freedom that are, you know, only weakly coupled, so the Hamiltonian is approximately a sum over terms associated to each of the degrees of freedom, then it's just a fact that we can approximate that state by another state that's very close to it, where the rank of the second state is at most e to the s plus something subleading in s. Okay, so sort of the von Neumann entropy of the thermal state captures at leading order the number of qubits you would need to sort of describe the state or to send a compressed version of the state to your friend Bob. There's another way of saying this, which is that the smooth max entropy of the state, the thermal state, is approximately equal to its von Neumann entropy. I'm going to define smooth max entropy in just a minute, but this for those who are familiar with it anyway, and those who aren't, then this is really just another way of stating the first bullet point in different words. It's exactly the same statement that you can approximate the thermal state by a state of rank e to the s. Okay, so the same thing is true for a pure state. In this case, the von Neumann entropy is 0, and it turns out that the smooth max entropy is also 0 just because you can approximate the pure state by itself, which is a state of rank 1, i.e. e to the 0. Okay, so same statement is true as for the thermal state. However, if I have a mixture of the two, then if I want to be able to approximate that mixture from the two with high accuracy, then really I also need to be able to approximate just the thermal state itself, right? Because the approximation can always be written as a sum of something that approximates the pure state plus something that approximates the thermal state. This means that the smooth max entropy of the state, so I should have shown these definitions of smooth max entropies earlier, but the smooth max entropy you can really just think of as being, by definition, the how small I can make the log of the rank of the state in some approximation rho tilde that's close to my original state rho. Okay, so for this mixture of the two, then the smooth max entropy is equal to the von Neumann entropy of the thermal state, and this is not equal to the von Neumann entropy of the mixture. It's equal to the von Neumann entropy of the mixture divided by 1 minus p. Okay, so it can be a lot larger than the von Neumann entropy of the mixture. Similarly, you can define a smooth min entropy, which will show up later and play a sort of equal and complementary role to the smooth max entropy, as just how small, how big I can make the log of 1 over the largest eigenvalue of rho without changing the state rho very much. Okay, so the smooth min entropy is about how small I can make the largest eigenvalue. The smooth max entropy is about how small I can make the rank. One way to think about this is that these are giving you like upper and lower confidence bounds on the sizes of the eigenvalues in rho. Okay, the von Neumann entropy is capturing sort of the size of the average eigenvalue. These are like upper and lower confidence bounds. These are giving you error bars on the size of the eigenvalue if you choose an eigenvalue at random. Hopefully that's clear to people. If it's not, definitely ask questions. Anyway, the general rule will be that these sort of large corrections are going to show up sort of whenever you have these incompressible states where like the smooth max entropy is much larger than the von Neumann entropy. Similarly, when the smooth min entropy is much smaller than the von Neumann entropy, the conditions are actually equivalent. So these sort of incompressible states, if you want to encode them and send them to someone, then they need a lot more degrees of freedom to successfully send it than the entropy of the state might suggest. Okay, it's a lot more than the dimension. You need a Hilbert space that has a much larger dimension than e to the s. And what we're going to see is that sort of for this information to successfully make it all the way to the boundary region big B, and hence for the entropy of that region to sort of show up in the QES prescription, then it needs to sort of get compressed enough to be able to make it through the quantum extremal surface. And so, yeah, that's why this condition is going to show up. But I will make this a lot more precise in a while. Okay? So unless anyone has any questions, then what I'm going to do for now is I'm just going to, ignore the sort of general case and just take this particular state that we considered and actually a slightly simplified version of it, and then just do the replica trick calculation to find out what the von Neumann entropy actually is for this mixture of the two states. And what we'll find is that it is indeed P times A1 over 4G plus 1 minus P times A2 over 4G. Okay, so we get the sensible answer that agrees with linearity and standard entropy bounds and so on, but does not agree with the QES. Okay, so lightning fast review of the replica trick. So we want to calculate von Neumann entropys in the QFT and the gravity and stuff like that. And the only thing we really know how to do in those things is path integrals. But computing a von Neumann entropy directly using a path integral is hard. So what you instead do is you compute what's called integer n Rayleigh entropies, given by this formula. And these are really just like trace rho to the n is really just an observable on n copies of the system. And observables can be computed using path integral. So you can compute this using path integral, and then you can analytically continue to the limit n goes to 1, and that will give you the von Neumann entropy. Okay, so particularly in ADS-CFT, this gives us a set of rules for computing von Neumann entropies. The first thing we need to do is work out how to evaluate trace of rho to the n. I'm going to start by talking about what you do on the boundary side. So in general, states in ADS-CFT are prepared using Euclidean path integrals. Okay, so in trace rho to the n, we have n copies of the density matrix. That means we have n bras and that we have n kets. So just to construct rho tensor rho, then we need to have sort of 2n Euclidean path integrals. Okay, I've drawn them schematically like this, all these things. And then what we want to do is that we don't want, so that sort of gives us like the global state for each of the copies of rho. But what we want to do is we want a partial trace over the things that aren't in B. Okay? So what does that mean in the path integral? It just means you glue those parts together. So we take these boundaries of the path integral, B bar here, and we glue it to B bar here. Similarly, B bar in this copy here gets glued to this copy here. These are the bras are on the top and the kets are on the bottom. And the same in all the other n copies of the state rho. Okay, so now we've got a tensor product of n copies of the reduced state. But now we want to turn that into trace of rho to the n. And the way to do that is to now glue the B boundaries together. But rather than just gluing them in pairs again, which would give us trace of rho itself fall to the power n. We want to glue them in a way that sort of cyclically permutes them. So this first ket gets glued to the second bra, second ket to third bra, and so on all the way around. Finally, we want to convert this boundary prescription into a bulk prescription. And the way to do that is just that we integrate over all bulk geometries that have these boundary conditions. With G Newton small, this calculation is going to be dominated by a saddle point. So really, we just have to sum over all the saddle points that have these boundary conditions. Okay, unfortunately, in general, computing these saddle points is hard, but there's a particularly simple class of states where you can do it, which are called fixed area states. So what are these fixed area states? They're just states where you prepare the state, and then you measure the areas of all these extremal surfaces. These areas are fixed, be some particular value. What does that mean? It means in the path integral, you no longer need to integrate over the areas of these extremal surfaces. And that in turn means that if you look for saddle points of that path integral, then those saddle points can have conical singularities that sit at the extremal surface. It means there's a whole class of saddle points where the bulk geometry is just the original bulk geometry with n equals 1, except that we have branch cuts that sit at these extremal surfaces that sort of permute the different copies of the bulk geometry, that glue together different sheets of the different sheets of the bulk geometry at the extremal surface. I'll make that more precise in the next slide. Great thing about this is that because everywhere except for near these surfaces, then the geometry just looks like the original n equals 1 geometry. When we normalize the states by dividing through by trace of rho, that cancels the contribution from all the gravitational action except for the contribution at the conical singularities, right? Because the conical singularities only exist in the geometry where we're gluing together the different sheets. These conical singularities give a contribution to the action. It just looks like the sort of conical excess times A over 8 pi g, where A is the area of the surface. Because our boundary conditions glue together sort of big B bar to the same sheet on the bra, then as I go up through the bulk, through this region that's sort of near to big B bar, then I have to stay on the same sheet. Otherwise, my boundary conditions will be right. Similarly, for this region near big B, then if I start on sheet 1, I have to end up on sheet 2. If I start on sheet 2, I have to end up on sheet 3. So when I go through this sort of region near big B, then the sort of permutation that gets applied that mixes together the different sheets has to be the cyclic permutation, which I've called tau. Okay? But if I go up through the sort of central region between the two surfaces, then I'm not constrained by the boundary conditions. The boundary conditions don't constrain how the different sheets get glued together. In fact, I can have some like arbitrary permutation pi that permutes the different sheets. So if I start on sheet 1, I could end up on sheet 4. If I started on sheet 2, I could end up at sheet 3, start at sheet 4, end up at sheet 2, and so on. Some arbitrary permutation pi. Okay, and I'll still get a solution to the equation of motion. It will just affect what sort of conical singularities I have on these extreme surfaces. But that's fine because that's allowed by the saddle points now that I've measured the area of those surfaces. So in the bulk path integral, what we're going to do is just sum over the saddles that correspond to all of these permutations. Okay, there might be other saddles, but like there aren't really any obvious ones, and certainly this is a natural class of saddles to sum over, and it will, when we sum over this class and then analytically continue, we'll get sensible answers. When you do this, you get a formula for trace of rho to the n, which just looks like sum over each of the saddles, labeled by permutations, times this contribution to the gravitational action that we get from the conical singularities of the surfaces, plus the sort of contribution from doing the path integral over the bulk fields, which just gives us, it's just give us the expectation of these operators tau and pi that permute the different sheets. Okay, so it's just a trace of n copies of the bulk state times some permutation operator acting on the bulk regions little b, this region here, and little b prime, which is the center region. In general, this sum over saddles will either be dominated by the permutation tau or just the identity permutation. If we drop everything except for one of those two permutations and then analytically continue this answer, then we end up getting this sort of naive quantum extremal subscription. Okay, that's the standard Lukowitz about as seen in derivation. In this case, for fixed area states, goes back to Dong, Harley-Maroff, and Akers-Rao. However, we've already claimed that that gives totally the wrong answer in this case. So the obvious thing to do is just not drop all those terms, keep this full sum, and then try to analytically continue this full sum. All right, let me make a couple of comments about this formula. So this gravitational action that comes from the conical singularities is controlled by these quantities C of pi and C of tau inverse pi to just number of cycles in those respective permutations. Just turns out that the number of cycles in the permutation controls the sort of total amount of conical excesses you have, which controls the gravitational action you get. Key point is that these areas, A1 and A2, are formally infinite. They diverge as I take my boundary cutoff away during. What does this mean? It means that saddles that don't maximize the sum of these two quantities are actually infinitely suppressed, right? The difference A1 minus A2 is finite, but the individual areas are infinite, and the sum is infinite. So if I'm not maximizing the sum of these two things, then I'm just going to get a contribution that's infinitely suppressed compared to the leading. So we can just forget about any saddle, any permutation pi that doesn't maximize this sum. The remaining permutations that do maximize that sum are in one-to-one correspondence with what's called non-crossing partitions of a disk. I'm not really going to get into what that is, but the key point is that it's just some subset of permutations that we can call non-crossing permutations. Now we want to take this sum over these remaining non-crossing permutations and analytically continue it to n goes to 1, so that we get the bond line. This is where we have a problem, which is the number of terms in this sum depends on n. Okay, so the number of permutations pi in Sn depends on n. In this case, we're just looking at a subset of those permutations, but the number of permutations still grows as we change n. In general, if I just have sum over, I have some function for integer n, where for each n it's a sum over a different number of analytic functions of n, then it's not obvious how to turn that into an analytic function that we can then continue to non-integer values. Fortunately, in this particular case, because this state is kind of simple, well, for the formula I've written there, then there's not a way that I know of at any rate to do this analytic continuation. But for the particular simple states that are just sort of a mixture of two, where all the entropy is sitting in region little b prime, and we can forget about region little b, then we can in fact use some technology from the theory of free probability that lets us indirectly analytically continue this sum and work out what the answer would be. And this goes back to my paper with Douglas Stanford, Steve Schenker, and Jianbin Yang from last November. So how does this technology work? Well, it uses this thing called the resolvent, which is just defined as the trace of the inverse of lambda minus rho. Okay? Where lambda here is just some positive scalar. This can be Taylor expanded, and we see that this resolvent is just controlled by the values of trace of rho to the n. Okay, so it's reasonable to hope that knowing how to compute trace of rho to the n might let you compute this resolvent. And in principle, of course, it does. And if we can compute this resolvent, then by taking its imaginary part in the limit where sort of I epsilon goes to 0, we're able to find the eigenvalue distribution for rho, and then we can find everything, including the bond diamond entropy of rho. Turns out that using some clever tricks, then this equation for the resolvent in terms of trace rho to the n, combined with the formulas for trace rho to the n for the particular bulk states that are just a mixture of sort of pure state and thermal state, then you can find a recursion relation that is satisfied by the resolvent. And that recursion relation, you can think of this like a Schwinger-Dyson equation, that's really what it is just this particular equation here. Okay? You can see that our paper from November or the paper coming out in a couple of days for details how this derived. I don't really have time to go through it. But suffice to say it can be done. And this resolvent equation, once you multiply out the denominators, is just a cubic equation. So it can be solved in principle. But no one ever got any insight out of using the general formula for the solution of a cubic equation. So instead, what you can do is you can approximate it in different regimes to get quadratic equations. Quadratic equations actually have a solution that's useful, not just a solution that exists in principle. So what you notice is that this term, second term in the denominator and this third term in the equation, the second term is very, very small compared to the first term unless r is really, really big. So at small r, we can just forget that that term exists. What about if r is really, really big? Well, if r is really, really big, then this term is much bigger than this term. And so we can ignore this term at sufficiently large r. And because we made this entropy S very big, there's an overlapping range of values of r where we can ignore both. So these two approximations have overlapping regimes of validity, and in each case they give a quadratic equation which can be solved just by, and in particular you get a non-zero eigenvalue density whenever the discriminant of that quadratic equation is negative. Hopefully that is familiar to all of you from maths lessons in high school. When you use these solutions, you find there's sort of one peak of eigenvalues that appears in each of the different approximations to the resolvent. So the first one is a load of eigenvalues that have size p times e to the minus a1, and there's e to the a1 eigenvalues that look like that. So these are the eigenvalues that come from the pure state within the mixture. Right, the total contribution to the state is sort of the trace of these eigenvalues gives p, right? So that's coming from the probability of that pure state. We also find a load of other eigenvalues, namely sort of e to the a2 minus e to the a1 eigenvalues that have size 1 minus p times e to the minus a2. So these are the eigenvalues that come from the thermal part of the mixture. They're size e to the minus a2 because that's the size of the eigenvalues in the thermal state, and their total, if you integrate over them, they're given 1 minus p contribution to density. That's the contribution to the thermal state. Now we have this answer. It's really just a very simple matter to just do the integral and work out the entropy, and you indeed get the answer that I claimed you got, which is that the sensible answer consistent with the fact that it's a mixture of these two states, right? That just has to happen because the state itself is a mixture of the two things. So great, we got something that wasn't the QES prescription and resolved these contradictions that we had. Yay. But that was just for some very particular state. More generally, we'd like a general set of rules for when large corrections will exist to the QES prescription. So for slightly more complicated states than the ones I just talked about, you can still approximately do the replica trait calculation and you just get an answer. Sort of generalization of the thing I just said. But for completely arbitrary bulk states, in particular bulk states that have some complicated entanglement structure between sort of little b and little b prime and little b bar, like all the different sort of bulk regions separated by the extremal surfaces, then the current tools that we know about are just not sufficient to do the replica trick calculations. So that's unfortunate. But the good news is we can sort of get around this fact. And the way that we get around this fact is we note that the formula that I found in the previous section for trace of rho to the n for fixed area states in gravity happens to be exactly the same formula, including the full sum over permutations pi, as the formula for trace of rho to the n in a particular very simple random tensor network, which is just this tensor network I've shown here. We have some bulk states, on little b prime, and little b bar, and then the one on little b prime gets input into a random tensor with output dimensions db, which is going to equal e to the a2 over 4g, and db bar, which is going to equal e to the a1 over 4g. And then we just take those degrees of freedom, add in the ones from little b and little b bar respectively, and then just apply some random unitary or whatever, and get an output on state big B. Okay, so this really is, the people who are familiar with the standard analogy between random tensor networks and ADS-CFT. This is exactly the tensor network you would want to be roughly analogous to the setup we have. And it genuinely does just give the same formulas for trace of rho to the n. So what does this mean? It means that if we can calculate the entropy of rho b in this random tensor network, even if the way we calculate it has nothing to do with any replica tricks, then we have necessarily also done a replica trick calculation for fixed area states, or worked out what the replica trick answer for fixed area states would be. That's just because the replica trick answer for fixed area states has to be the same as the replica trick answer for the random tensor network, because it's the same calculation mathematically, which in turn has to be the same as the answer we get in other methods for the random tensor networks, because maths is consistent. Okay, and magically, one-shot quantum information theorists, this is their bread and butter, computing things like entropies for something that looks like this, and they can tell you exactly the conditions for when you have large corrections and when you don't. So this gives us a sort of new refined set of conditions for when the QAS prescription holds and when it has corrections. So I'm now going to just tell you what that is. And then what I first want to do is rewrite the naive QAS prescription in a slightly unusual way, which is we can say that it says that the entropy is the entropy area A1 plus the bulk entropy of little b and little b prime whenever the conditional von Neumann entropy of little b prime conditioned on little b is less than the difference between the two areas over 4g. Okay, so that's just a slightly unusual way to write it. I've written it in terms of this conditional von Neumann entropy, but it's just the standard formula. Yeah, and if conditional von Neumann entropy is bigger than the difference, then we get area of A2 plus S of little b. Okay. The reason I wrote it like that is that that's going to be the natural way to define this refined set of conditions for QES, which is just that this top formula is only true when not the von Neumann entropy, conditional von Neumann entropy is less than the area difference, but the conditional smooth max entropy is less than the area difference. And similarly, for the bottom formula to be true, we need the conditional smooth min entropy to be bigger than the area difference. However, there's some intermediate range in principle where the min entropy is smaller, but the max entropy is bigger. And in that case, there's just not some simple rule. It's going to be smaller than either of these two quantities on their own, but in general, it can be some pretty complicated thing. It will depend on the details of the sort of whole spectrum of the state, not just its entropy. So as I say, these H min and max are the conditional versions of the smooth min and max entropies that I introduced before. Their definition is unenlightening, so I'm not going to waste time on it. But the key point is that unlike this conditional von Neumann entropy, these things cannot be written as just a difference between, you know, two unconditional smooth min and max entropy. Okay. So the intuition, which I'll go back to in more detail in a bit for why you should think that this is sensible, is that H max in a particular sense captures the number of qubits that are needed to communicate the state on little b prime to someone who already has access to the state on little b. Okay, that's going to be what's called quantum state merging. I'm going to find it more properly later. So what this top condition is telling us is that sort of the entropy from little b prime only ends up in big B if there's sort of the difference between the entropy is big enough, difference between the areas is big enough that there's sort of enough qubits available for the degrees of freedom in little b prime to get transmitted all the way to big B. So that's just some vague words. I will make that intuition more precise. But then what's the intuition for this other condition with H min? Well, it's just a fact that if I have a pure state, then H min, a pure state on little b prime, little b bar, then H min of little b prime conditioned on little b is just minus H max of little b prime conditioned on little b bar. So like a generalization of the fact with conditional entropy that S of little b prime given little b is minus S of little b prime given little b bar. Okay. So this second bottom inequality can be thought of as being about whether H max of little b prime given little b bar is less than A1 minus A2, i.e. whether big B bar ends up knowing everything about little b prime. I'm going to again make that more precise later. So as I've said so far, this is only an argument for this sort of prescription being true in fixed area states. And obviously, in general, we want to consider states like, say, the vacuum state or the vacuum state with some turbulent matter or thermofield double states and stuff, where the areas of the extremal surfaces are not fixed, right? And in this case, the replicated geometries involve a lot of back reaction, and they're very hard to find explicitly. However, we can deal with these sort of general states by just writing them as a superposition over polynomially many fixed area states. And by similar arguments to my original claim about how the sort of entropy of a mixture had to be given by the expectation of the entropies of the states in the mixture, this means that up to small corrections, the entropy of the semi-classical state ends up having to be given by the expectation of the entropies of the states in the superposition. It's a slightly non-trivial fact that involves facts about how areas can be reconstructed on the boundary subregions, but it is true. You can read the details in the paper. Hence, at leading order, we find exactly the same sort of corrections or no corrections to QES for semi-classical states that we found for fixed area states. So the same refined conditions. Okay, so the final part I want to talk about, and there's really a load of this paper that I'm just not talking about at all. So I encourage you to check it out. I mean, I would, but I do when it comes out in a couple of days. But I just want to talk a bit about how this connects to entanglement wedge reconstruction and explain more the slightly cryptic comment I made about quantum state merging. Okay, so what is entanglement wedge reconstruction? Well, basically it says everything between the minimal quantum extremal surface and the boundary is encoded in that boundary. Okay. So the more precise version you can make that sort of, we call state-specific EWR. That's really about a particular bulk state row. That's that given a bulk state row and a bulk operator acting somewhere in the bulk, then we can find, as long as the bulk operator acts within the entanglement wedge, then we can find a boundary operator on B whose action is the same that does the same thing to a purification of the bulk state rho as the bulk operator. Right? The bulk operator and the boundary operator do the same thing when acting on a purification of rho. If I make rho be the maximally mixed state in some subspace, some code subspace, then this is the usual definition of entanglement wedge reconstruction, that it needs to do the right thing for states in the subspace. Using this sort of state-specific definition of EWR, then what you find is that the condition for reconstructing bulk operators in region little b prime is exactly the same as the sort of condition we found for the QES prescription, which is that the smooth conditional max entropy of little b prime conditional little b has to be less than the difference between the two areas. Okay, so what does this have to do with this thing called one-shot quantum state merging? Well, one-shot quantum state merging is the following task. You have some state rho AB that is shared between Alice and Bob, and you want to transfer Alice's part of the state to Bob by sending as few qubits from Alice to Bob as possible. And what I mean by transfer, and there's a couple of definitions, the most standard one is so that if really the state rho AB is purified by some system C, then Bob ends up with a purification of system C. Okay. This is really just a Schrodinger picture version of entanglement wedge reconstruction. Entanglement wedge reconstruction, we work in the Heisenberg picture in terms of operators, is really just the same thing. The part of the state that is initially held by Bob corresponds to region little b, just like easy for region big B to reconstruct. The parts that's initially held by Alice is the bulk state in region little b prime. And the question of whether you end up being able to reconstruct little b prime depends on whether enough information about little b prime got through the quantum extremal surface to be reconstructed when you already have access to the information in little b. The minimum number of qubits that you need to send to do one-shot quantum state merging is exactly this smooth conditional max entropy. So it's exactly the same thing that we found in EWR, needed to be less than the area difference. But the maximum number of qubits from region little b prime that can be you can learn about from region big B, boundary region big B, is indeed the difference between the two entropy, the two areas, A1 and A2. That goes back to a paper I wrote with my advisor, Patrick Hayden, a couple of years ago. So what we find is that gravity uses exactly the minimum number of qubits that it needs to achieve this task of one-shot quantum state merging. If it was able to achieve this task using the usual entanglement wedge reconstruction conditions, then it will violate the bound on the number of qubits you need to send to be able to do quantum state merging. So there's sort of an important point that I glossed over when I talked about the number of qubits for quantum state merging, which is that when you do quantum state merging, it's crucial that you allow Alice to send an unlimited amount of classical information to Bob. It's only the quantum information that you limit the amount you can send. In gravity, there's not a large extra large amount of classical information in region little b prime that can be transmitted to region big B. That was computed by Ningbao and Hiroshi Okori. There's actually no additional classical information on top of the quantum information. But what there is there's what's called additional 0-bit information from region little b prime that gets through. This is a sort of weaker form of information than classical information, but it turns out it's still sufficient to do quantum state merging. In fact, it's the minimal information you need to do quantum state merging. And so this is what gravity uses to do the quantum state merging. So gravity has exactly enough information to be able to do entanglement wedge reconstruction once you replace the sort of traditional condition by this refined condition using the smooth max entropy. Okay, so I just want to make some brief final comments. This is really all I have to say in the talk. Hopefully you got something out of it. So the first comment we want to make is that the replica trick is cleverer than the quantum extremal surface description. The quantum extremal surface description is incredibly nice and clever because it just uses the original unbacked reactive geometry. But if you can do the replica trick, then it does tell you more about what's going on. A second point, which I haven't really emphasized, is that there was always a weird oddity from a quantum information point of view, which was that holography only involves a single copy of a state row, right? You don't have some large tensor power row. Yet von Neumann entropies seem to be playing a crucial role, even in things like entanglement wedge reconstruction, where you didn't put in that you wanted to think about the von Neumann entropy, but somehow the bulk von Neumann entropy was showing up. Yet in quantum information, the von Neumann entropy plays very little role in the sort of one-shot setting where you don't have a tensor product of a large number of copies of the state. There's a couple of like very minor operational things where it's the right answer, but overwhelmingly the right answer involves like these smooth min and max entropy variations thereof. So the nice story of our paper is that it resolves all of this. That really the things that mattered were always the bulk smooth min and max entropes, just like in ordinary one-shot quantum mechanics. It just so happened that the states we normally considered, like thermal states and so on, those smooth min and max entropies happen to be equal to the von Neumann entropy up to small corrections. So we could get away with using this sort of coarser characterization of the state, namely the von Neumann. So yeah, that's really all I have to say. So thanks very much for listening. As I say, I hope people got something out of it. Yeah, thanks a lot.
Yeah, thanks very much, Geoff, for a very beautiful talk. Questions? Seems like we don't have any questions.
Good.
Hello? Yeah.
Hello? Yeah.
Yeah, please. Oh, okay. No. I think it was a member of the audience.
Sorry.
So,
Oh.
yeah, Karan, please go ahead.
Yeah. Yeah. Sorry, my mic was off. Yeah. So I'm just curious about this. So you're saying when you're taking these corrections, there's some kind of continuation. Like I didn't get that part in the middle where you're saying that for all regions which are different than the H max and H min, it depends. That's sort of what you mentioned, that it depends on what's going on. So is there like a continuous version now which goes from one surface to the other surface in your prescription? Is there some notion of that?
So yeah, so let's just take the case where the state in little b prime is not entangled with the state in little b. Okay, that's the simplest version where you can actually be very explicit. Okay, then what you do is you just look at the entanglement spectrum, okay, of the state in little b prime. And you can divide that up into two parts. You can divide it up into the eigenvalues that are larger than e to the minus the area difference, and the ones that are smaller than e to the minus the area difference. Okay?
Mm-hmm.
And then what you get basically is that you get the probability of having an eigenvalue that's larger than the area difference times this formula, plus the probability of being smaller times this formula. Okay, so as I make
so P in your formulas, that P is sort of fixed, is it? I mean, you had a P of A1 by 4 plus 1 minus P A2 by 4. So that P is
you can imagine varying that. Yeah, I can imagine. I mean, P is just saying how much of like the particular state is a mixture of the two, and it's like how much I have of each state. right? So I could imagine changing the bulk state so that P changes.
I see. Okay.
Yeah, and as I do that, I'll continuously go from one
Right.
end to the other end, right?
Okay.
Yeah, but the point is you don't have a sharp transition from some sort of this formula to this formula. You gradually change.
Okay. Yeah.
Great.
Thanks.
Okay. Are there any more questions? Anyone raise his hand?
So,
okay, there are no more questions. Yeah.
I just have a quick question. So what happens if you have a non-equilibrium situation in the bulk? Does
Yeah, no, that's a very good question. That I glossed over. That this is all, this all sort of needs a moment of static of time symmetry for it to, this rule in principle you could apply even for non-static situations, just where you say A1 and A2 have to be the two extremal surfaces. But if you have, say, more than two extremal surfaces, then we have a rule for the static case. But I don't really know what the sort of rule should be for the time-dependent case. Yeah, like it would be nice to have some sort of like maximin style prescription. That already the rule when you have an arbitrary number of extremal surfaces gets kind of complicated. And there's sort of a large number of conditions you need to check to see whether the QAS prescription applies. And yeah, I think that's the task for future work, to work out exactly what the most general refined rules are for time-dependent situations.
So it could be that the QES naive prescription does work, but for some time scales and maybe not work. Is that?
I mean, yeah, I mean, certainly if you look at the state at different times, then yeah, it can, the QAS prescription itself changes, and whether it needs to be refined can also change. That's certainly going to be true. Yeah.
Can I ask
An
one
example
more?
would be, yeah, go ahead, sorry.
So could you motivate a little bit again these fixed area? When you were doing the path integral, you wanted to focus attention on only the fixed area.
Yep.
What's
yeah,
the
so the motivation is purely practical, that you can actually do you can do the replica trick with the full sum over saddles for fixed area states. For non-fixed area states, then even computing all the saddles is hard. Basically, you for non-fixed area states, the only thing anyone knows how to do is the Lukowitz-Mauducci trick of like, just assume you have one saddle which is an analytic function of n and which doesn't break replica symmetry, and then you quotient by the replica symmetry, and then you analytically continue to n equal close to 1, and you argue that you get back close to the unbacked reactive geometry and blah, blah, blah. But doing that gives you the naive QAS prescription, right? So we to avoid getting the naive QAS prescription, we clearly need to be more careful and not drop all the extra saddles. But I just have no idea how to do that calculation except in fixed area states. So that is purely practical, but then it is also true that any state can be expanded in terms of fixed area states, just like you can expand any state in terms of any particular basis. Yeah, if you by doing so, you can argue that the answers for the fixed area states also tell you, at least a leading order, what the answers are for the non-fixed area states. So yeah, it's purely a technical, practical consideration.
Thanks.
Okay, so if there are no more questions, we will thank Geoff, and it's over to Urban for closing remarks.
Thanks very much.
We sincerely thanks all the speakers from both today and yesterday for excellent and wonderful talk. And we hope that we can organize some of this workshop again in future. Also, I thank my co-organizer, Shubho and Arindo, for helping me with this. And also I should thank IIT GN and the excellent staff who actually helped us with this, making the web page and also the Zoom support. I sincerely thanks them. And again, thanks everybody. We end the workshop here. I hope that you all have enjoyed this.
Thanks to the organizers. Thanks.
Thanks, Prem.
Thanks, Ram.